Board. Which way is clear? Oh. Should I explain using the pen on the projector or should I explain on the board?
This is my first one I've shown up to,
Oh, right.
so I don't know how you've been doing it.
I usually used to explain on the board, but people on Zoom weren't seeing well. So since more people are starting to show up, I wanted to encourage like recording it as well and making it available on Zoom and on real life. And I can't hear people on Zoom because when I put my headset in, I keep hearing myself, so it's very annoying. So hopefully, if somebody joined in Zoom, they will send a message or something. But yeah.
Is that what I'm hearing over there? Whenever you speak, I can hear it through your phone.
Yeah. Like, slowly. Better for everybody. So if somebody joined, somebody joined in Zoom, hopefully we can hear them through the phone. I'm trying to figure things out. Should we start with homework, focus on homework 3? Right. So the new idea, since more people are starting to show up, the goal of the TA hours is for it to be a discussion. But to make it practical for everybody, usually we start a discussion. Tuesday will be like fully discussion. Thursday will be more of like the problems we got through Tuesday, the repeated issues we had. For example, some people had issues with at least mine. I will try to do them today and record them, make them available online, and as well have a discussion. And Friday will be also fully discussion. So during discussion, it's more of a like 50-50. Like we ask questions, feel free to interrupt me, tell me I'm wrong. Like, it's your time, right? And also, if you have any comments regarding how are we doing things, that you prefer on the board, you prefer it, just feel free. I'm like, I'm cool with anything. Mhm. Hi. Can everybody see the board? Yes. F5, F5. What's this? Can everybody see the board? Is it clear? All right, so we'll start with homework 3. So the first question is asking you to, do we have a coaxial cable modeled? This is available in your notes, in your reading materials. Describe the impedance matching or mismatching in your own words. I think I should leave this part out, but you should have, or we will come back to it later. So you can read the notes and see what you understand from impedance matching and mismatching. Then next thing we'll try to reproduce those figures using LT spies. So we can directly start with LT spies. Despite if we had time, we can go for how to exit slide. So If we have time, we can go for general description, but we just start by opening LT spies. Let's bring it here. Do you guys prefer I design it step by step or just open the design from something I had previously? All right, sure. So you start by opening a new schematics. If anybody has any problems, like feel free to ask even something simple. So that's LT spies. I'll be using the shortcuts for it to be similar for people who have Macs or people who have PCs, but you can see that you can you'll have components up here, either in edit, you can pick your components, or you can just remember the shortcuts. So for example, if I want to insert a resistor, I'll press R. If I want to rotate it, I'll press Control R. Or let's delete this resistor. So I have an inductor, capacitor, and a resistor. So for an inductor, I do press I, escape, I press I, or I press L, Control R to rotate. Then I want to put a capacitor, and then a resistor. I press R for the resistor. We'll input wires. You press W. So you can either you go for escape. You can go for edit wires or W or F3, depending on the version of your LT SPI. Some people have a W, others have it F3. I think this laptop is F3. All right. So I think I should have brought a mouse. So you guys, like, it's easier to deal with a mouse. Now I have to put a voltage source, but as you can see in this examples, we have no voltage source. We'll discuss what kind of source we're gonna put. But before this, let's define those values. So one smart trick I'd like to use is to define them as variables and define all the variables down here. So I'll insert a command. To insert a command, you press dot, or you can go for edit, OP spice directive. Oh, it's S spice directive. Here it's S. On my desktop, it's dot. And then, so for this command, I'll call it params, P-A-R-A-M-S, and I'll name my parameters. So I'll name R1. Let's make it 50 as shown here. And L1 is 97.5. L1 equals 97.5. That's nano times foot. And C1 equals 39 pico times foot. Now, let's define foot as 3. So those will be my parameters. You can manually define them for each element, but when you want to change something frequently, sometimes it's more organized to do it this way. In bigger circuits, you'll find it easy. To define those as variables, so you click on the value of the element. You don't click on the name. So this is the name of the element, and this is the value of the element. You just right-click on the value, and you call it. Do you guys have any?
Oh, just see it.
Sure, sorry, it's fine, definitely. Yeah, this is. I don't want to make this a class. I wanted to keep it as a discussion. So you name those elements as the name of your variables. So this is called L1. You right-click on the value, name it C1, and right-click on the variable, name it R1. So currently we just copied the circuit, developed it and everything. Then here they mentioned if L is equal 3 feet, we defined L as 3. As you can see here, if L is 3. In rectangular form, find. So we want to find the AC simulation or the AC analysis. So what kind of source do you guys think we should put? Should we put a voltage, or should we put a current, or should we? Yeah, so you can go for edit, spice directive. So for some people, they have it S, others they have it dot. You just press in your keyboard. And for some people, they have it, the shortcut is somewhere here over the end. Yeah, welcome. So we need to put a source for this circuit to run. It doesn't matter actually, because the simulation we're trying to solve for is ZEQ. We're going to solve for the equivalent resistance. So you can put either a current source or a voltage source. But I found some trick is that since we are solving for ZEQ, and we know that Z is equal to the voltage over the current, should we try annotating? So is it cool to annotate like this? Annotate. Right. Pen. So if this is our circuit, we need a source here, and this is our ZEQ. We know that ZEQ is equals to V total over I total. This is given, right? So we can define I total to be equal to 1, and then just solve for our V here, because in LT Spice, in theory, you cannot get Z directly. So if you solve for V, it will be Z. It will be like the value of Z. So that's clear, or we can just leave it. So I'll insert a current source. To insert a current source, we go for edit, component, or I think sometimes, yeah, component. I have a big difference in the symbols between my laptop and my desktop. So I'll insert a current source. You can search for CURR, current. Okay. Control R to rotate it. Just insert it. And F3 for wires, or W. So we are doing right click, F3 again. We got the ground, G. Right click on your current source and press advanced. So what value do you think we should give it? So for the AC amplitude, we'll give it a value of 1. It doesn't matter any value will do, but we said, like, for calculation purposes, to make our life easier, we just put a value of 1 without any phase. It's we don't need to mess with this part, since this part is for DC. We are doing an AC analysis. We just press OK. Simulate. What kind of so you can insert simulation command. So we're gonna do an AC analysis. Let's check our notes. Let's see our sorry, where is our notes? Introduction, course notes, summer. Let's clear our annotations. Clear our drawings. I should have brought a mouse. Was it page 80 something, 86? All right, so we can see what kind of results are we looking for? We are looking for an AC simulation using decade. So an AC analysis, type of sweep is decade. Number of points is 200. Number of points per octave is 200. Start frequency is 2.72059 mega. One mistake I made during the previous TA hours is I put M, and the results were totally wrong. M is milli. So it should, MEG is for mega. 27.205 MEG. It doesn't matter capital or small, but some for LT Spice, others it does matter. You press OK. Just place your AC analysis. All of this will be uploaded and will be put in the slides, and the slides will be uploaded as well. Like whatever is more beneficial for you guys. Just tell me how to make this easier. You just simulate, run. All right, so we can make this bigger. Let's enlarge our. So what kind of thing are we plotting? We're plotting ZEQ, and we mentioned that ZEQ is the total voltage over the total current. How can we get the total voltage? You just place a probe here, right? And how can we get the total current? You just place a probe here. So if you want to select the current, you place it on top of the element. If you want to place the voltage, you place the voltage in this area, right? Let's say you want to, you don't want to call it's, so the voltage at this point is called VN001. We can rename it as well. If you want to rename it, you can insert a node. Node. I can't find the node. There is a, like, you can insert the node and call the node anything. Can anybody see a node? No. All right. And for display purposes, if it's black because it's not very clear, you can. All right. The LT, there is a huge difference between versions of LT spies. Add plane automatic. Blah, blah. Okay, I'll go back to this later, but you can change the display color. Different LT spies have different arrangement of things. But so this is our voltage, and is it clear? This is our voltage. Let's see if it looks similar to the one we had. It does. Fit. There is a way to fit on. So it does look similar, but his simulation goes for our stop at 30 megahertz, our stop at 20 point something. His goes further. So let's change this as well. Make our simulation go for. Right. So instead of 27 mega, make it 50 megas. Yeah. Oh, yeah, you're right. Maybe that's a mistake as well. Thanks. 50 meg. Yeah. I don't know how it managed to run with this. That looks bad. All right. Well, another thing you can see, another difference is that our scale is in dB, and his scale is in. So what do you think that is? That's a linear scale in ohms. So to change our scale, you can right click here, and it's a both linear, and this is the range. So all right, our scale is in volts, and is in ohms. So you want to change it. So the ohm is volt over current. So first you plot the current, and you plot the volt. So right now we want to plot volt over current. You can do it manually, or you can click here and just go for volt over current. Is called I. Is it L1 or I1? I1. So that's the volt over current, and you can delete this. So yeah, so this should be the result. Doesn't look the same, but it should be, everything should be the similar. And by the way, I made a video for this questions and uploaded them on a YouTube channel, so you can watch like a shorter videos. Or if you want to check the videos, so I uploaded the presentation. I don't know why everything is PowerPoint. I cannot go for that. I uploaded this presentation. So gradually, if I for one question I answered in a video like this one, there is a link. You can just go for the link. and you'll find like the whole thing answered. But please, sometimes I change the value of I change the values, so it's not the values in the notes to make sure that you guys are following. So that's so you can go for it. You can watch the videos at your time. So the links are put them here, but once you find the YouTube channel, probably it will have all the titles with like with everything here. So it's titled with a homework number and everything. So it's titled with homework 3.2 discussion, and I will upload those notes as well. So that's the answer. Right. So as you can see, we got this. So you got the correct value using this simulation. And I check the values; they are the same. That's all you need to do. You just need to plot the voltage over the current to get the Z impedance. And to do this again, you can right click. There's add trace. And so, so first, you can plot the volt and plot the current, know what they are called, and then plot the expression. So we know that the volt at this point is called V N01. So that's so you write V N01 over I1, because this is the current here. And you just put it as an expression. So this is the expression, and this is your plot. Add plot and trace. Let's set visible traces. Oh, so in some computers, in my computer back home, the plot setting is somewhere else, but you can basically go for plot settings, and then you can turn on the color. You can edit. Right, never mind. You can basically change the colors of everything. I noted this in my video presentation. I'm surprised that the versions are different versions of LT Spice have different slight differences. So let's go for the second question. In my videos, I usually upload like more explanation. I try to match the circuits. Sometimes we have some fun. Are you guys familiar with this one, or should we do it as well? Right. Let's do it in 10 minutes. All right. So are you guys, you should all be familiar with MATLAB. That's all right. So you start by opening, so when you start, you can open either a new script or a new live script. Some people mentioned that they have their MATLAB version is limited. They didn't download all the toolbox. And for this example, we'll be using something from signal processing toolbox, I think. Some people, it's something called sawtooth function. Like some people, when they write sawtooth function, it doesn't work. The easiest way, you can either download MATLAB again, the same version from the website, and just add the toolboxes, add the signal processing toolbox, or add all toolbox, or you can use MATLAB online. You can just like Google MATLAB online and sign in with your account. You will have access to MATLAB on your browser. You don't need to download MATLAB even. So that's really fun. But for this example, I think it's very basic. So, but we're trying to generate this triangular periodic wave. So we mentioned that we found a ready-made function in MATLAB called sawtooth that takes some inputs and outputs for plotting the triangular wave. So the inputs it takes are the period. So in this example, the period is 20 E negative 3. Negative 3. And for this, all right, IA is equal to 1. So let's call it the amperes, or the amplitude equals to 1. amplitude. Let's enlarge this a bit.
You use semicolon at the end of line one.
It does it, yeah, we can use it or not. Like if you use semicolon, it will not display the result. If you did not, it will display it. See, I'm automatically getting confused between MATLAB and Python while writing. That's the problem learning them both. Yeah. So one is the amplitude, and we need to define a time, like an array for the time elements. So it's sampling rate, or let's make an f value fs, which is the number of samples per second. Let's make it 100 samples per second, where 1 over fs is our sampling rate. Now we'll define our time array that starts from a negative period. The number of samples per second is 1 over fs to 2 periods, for example. Like you can just mess around. There is no correct answer here. To 2 periods. Now let's plot the sawtooth function. Let's make a function called f underscore plot. And since this is a periodic function, you have to write 2 pi times 1 over t, which is our period, times our time, t. Let's plot this out. So figure plot x-axis versus y-axis. I don't know why MATLAB is not giving me suggestions. It used to, like, when you start a variable, suggest the rest. So grid on, you can put the x-axis and the y-axis and like be cool. So to run, you can just go for code run or Control-Shift-Enter. I thought my laptop is faster than this, but it's running very slow for some reason. Unrecognized function. Oh, fplot is equal. Yeah, something stupid we did. Fplot is equal. So AWTOOTH. Sawtooth. Wait. 1 over fs. Fs equal to 100. Why is it 7? So fs number of samples per time interval phi negative t 1 over fs. Fs. Let's copy this, but I'm not sure what we did differently here. Fs is equal to 10 and t is equal to negative t 1 over fs to 2 times t. Here's negative. Okay. So I think we need to increase fs. All right, because our signal is very short, our t is very small, so the number of samples per second should be larger because we need like higher sampling rate. So this is our sawtooth function. It looks different. If we want to change it, you want to make it into another kind of triangular function, you just add half. It should look fine. Let's say you want to shift this to the right or left. I'll not give you the exact answer for the homework, but let's say you want to shift this to the right or left. We mentioned in class that any periodic function can have a phase element. So minus phi or plus phi, whatever you prefer, it's just a notation. And let's make, you want to shift it to the right by like whatever, by pi over 4. Did it shift? Yeah, so you can adjust it. It doesn't matter in the final answer, but it looks similar to the one given. Yeah. All right. Thank you for bringing this out. Welcome. So the second thing we need to do is we need to solve for RMS. So let's try annotating in Zoom. Annotate. All right. So what's RMS? In your notes, RMS. Pen. When we mentioned this in our last meeting, so RMS is equal to the integration, all right, root of the mean. The mean is 1 over t, integration of the signal in one period. So it can be 0 to t, or I usually prefer negative t over 2 to t over 2, same thing. And then our signal, which is f of t squared. So this is our RMS. Can we move our RMS? Can we move our definition to the top here? Yes, we can. Let's do this in MATLAB. And let's plot every step by step to make sure our values are meaningful, our values are correct. Let's cancel the notation. So first we'll start by squaring the signals. We have ft squared. Can we ft squared? So we can take our ft plot. And ft plot 2 equal to everything squared. Will it give the right answer? Probably to the power of 2. In squaring an array, you have to square every element. So MATLAB, you do this dot notation. So dot, then to the power of 2. I think you guys should be familiar with this. And let's make another figure. Plotting f plot 2. Right. So take random variables, take the values in certain points and see if they are squared here or not. So at 0, 0 squared, 0 point, is it? Yeah, it's 0. At this point, 0 squared, which is, yeah, like you can check if this is the square of this signal or not. If you are satisfied with the result, so you need to take the root. So you did this part, you need to integrate. How do you integrate a signal? In MATLAB, there is a function called integral, but it takes its input a whole function. So you need to define this part as a function called f integral equals, how do you define a function? You just define the dependent variable and you input our function here. Dependent variable is t. So this is how you define a function. And to integrate this function, you just input it in FRMS. Let's do it in all one step. FRMS is equals to f integral FINT, or let's make it in 2 steps. FINT2 equals f equal integrate INT E G. Yeah, all right. So integral. See, I never memorized MATLAB functions. I just used the suggestions. Equal integrate of this one. Yeah, so you see, it needs an input argument. It needs a range. So you'll integrate it from t over 2. So f maximum to the minimum, 2 negative t over 2. I do not have a sense of this is the correct value or no, but in the end we will see. So after integrating, we will divide it by 1 over t and take the square root. So f underscore RMS is equal to squared SQ R, yeah. So MATLAB, one thing I like about this is they give you suggestions if you're writing correctly. The square root of f integral divided by t. Divided by t. Yes? should not be should not have a negative and positive component. It should not have an imaginary part. So something is missing. But if you guys want to check annotated answer, so I just did the same thing before coming to class here. So we defined it as a function. We integrated this function, f from negative t to t, and RMS should be equals square root of f integral. Get the square root of your function divided by t. Get the square root of your function divided by t. Let's test this out. So yeah. FRMS is equal to. Does it matter dividing inside or outside? Divided by t. Or something is wrong. I will get back to it, but I will provide this answer. So this is an explained answer in all the steps, but I put different values. So you just put the correct values you have in your lecture notes and you should be right. And I uploaded a video for this. I'm not sure why sometimes I get different answers when I do things in class than when I do it at home, but there is a video for this online. So let's go for the third problem. We can come back to this later after we're done. As you can see, we got everything is explained here well. All right. Do this problem by hand. Are you guys familiar with that? Should we do it?
It's a by hand problem.
Yep.
What will the count end up like looking like at it? Is it gonna be the real and imaginary value?
So it's asking, yeah. Or we can first explain the concepts. So let's say if you have a source. That's not here. That's right here. Let's have a quick discussion about what will power look like, and then try to solve it and see if we get something that's meaningful to us or not. So what do you think the power? So the power of a resistor would usually look something like this. Power of an inductor and capacitors usually look like something like this. So the average power of an inductor or a capacitor is 0, while the power of a resistor is usually it has a value. So this means that in general, if you have your circuit that has two elements, have resistors and capacitor, it will have a complex power. So as we mentioned in phasor representation, our total power will have a real component and an imaginary component. So our total power, I'm not sure, but some people use S, others use P. So usually P cosine theta and P sine theta. So power is something like this is our power in the end. It will be a phasor representation. But the main trick in power, and the something I did, somebody tried to correct me last time, and I insisted on my being wrong, is a power is equals to current times voltage, or V squared over R, or I squared, or I squared over yeah, I squared R. So it has lots of representations, but we are multiplying. Yeah, we are multiplying two cosine components. So I is usually our notation is in phasor. So it's magnitude I times V magnitude and V angle. But this is not, we are not directly multiplying in phasor. we are multiplying multiplying two cosine components. We are multiplying I cosine theta plus a phase. We are multiplying I cosine omega t plus theta 1 times V cosine omega t plus theta 2. So you guys can do this multiplication at your own time. It's very beneficial. But if you remember multiplying cosines, there is a trig identity for this. And then it will give you something different. So if you multiply it multiplied as a phasor, it will become I1 times magnitude of I times magnitude of V, and the phases plus each other. But in reality, if you multiply them as cosine, it will be the difference between the phases. Right? If you do the long way, in the end, it will be the difference between the phases. And another thing, depending on the definition of I and depending on the definition of V, if they give you RMS, in the end, you will have the answer will be I times V magnitudes. And the phase is theta 1 minus theta 2 over root 2. If they give you I peak to peak and V peak to peak, it's over 2. Why is it like this? Because if you do it in the cosine multiplication, you will find like in the identity, you will have in the end over root 2. You can basically prove it. Like if you have cosine A plus B times sine A plus B, it will be times sine X plus Y. It will be half cosine everything minus everything, and then plus cosine everything minus so there is a half here, basically, you can see. So we have a half here, so that's why we have half, or we have root 2. Sorry. Like if you don't trust me, or there is probably in chapter 9, this part is explained more, but we can go back to it or explain more details later.
The way that they format it to voltage of the source was kind of weird to elaborate on.
Oh, here?
It's like 10 UT, and I don't know what to do. Oh, U of T.
Yeah. All right. So let's solve it. Let's solve this question from scratch. Should we do it in Word better? Microsoft Word. So for this part, I highly suggest you refer back to chapter 9. Everything is explained there, but let's discuss it. Let's first turn off the annotation. Clear all drawings. Full screen. I want to quickly open chapter 9 for reference. I'm sorry, guys. Circuit analysis. So one thing I do for this class, I never memorize any function. It causes me lots of problems, but also makes me keep thinking about notations and whatnot, and like, is the circuit meaningful or no? Because if you memorize them, you like over trust yourself sometimes. You think like, yeah, I know this, how does it look like? All right, so this is chapter 9. As you can see, it started by explaining if we have an RLC circuit, like this is a shortcut, it can be the output, its output will look something like this. It's voltage. Let's see how does it. Yeah, it will have two components: omega node, which is the resonance frequency, and it will have alpha, which is the damping coefficient. It has another name as well. So you start by solving for omega node, the resonance frequency, and the damping coefficient. And based on those two values, your answer will have one of three shapes. It will either look like there was a table. No table here. It's probably in my slides as well. Yeah, your answer will look something like this. Based on the value of your alpha and omega, it will look. So this is for parallel. So you start by solving for alpha and omega, the damping factor and the resonance frequency, and then your answer will have a set value with two unknown variables, and you solve for those two unknown variables. That's the whole thing. Let's put those equations here to assist us. Should we solve it? So we start by getting the total R. Those two parallel each other. So we want to put it in either like in a series circuit or in a parallel circuit. We start by getting, so R total, R is equal to 1 parallels to 10. So 1 times 10 over 1 plus 10, which is 10 over 11. And C total and H total. So we start by solving for alpha and solving for omega, where alpha is, let's put all the equations in this slide so it's like a full answer. Alpha, alpha, alpha. Definition of alpha. This is chapter 9. Wait. As far as, yeah, here's alpha and omega. First, one quick definition of alpha and omega. What is alpha and omega signal? Omega is if you simulate this circuit in the AC simulation, you'll have result that looks something like this. So this will be frequency, and this will be amplitude. For example, it can be the voltage. So at this point, this is our omega node. This is our resonance frequency. Yes.
This doesn't have to do with the resonant frequency, but when you started the problem off, you said that the resistance would be 10 over 11.
Yeah.
Aren't the resistors in series, so wouldn't it just be 11? Or how are they?
Yeah.
Oh,
There is a trick about it, so you can take this part out and transform this part to like you can put it in a. I'll explain it later, but you can cut this part, and if you wanna make this resistor in parallel, yeah, but I'll explain for it later. But yeah, use source conversion rule. While alpha relates to a factor that determines the forced response from the steady state response. So this is the forced response, and this is the steady state response. So alpha controls this value. So like those are the value, the meanings of alpha and omega. So we start by solving for omega is equal to 1 over root LC equals to 1 over 2 times 0.5, 1 over 1, which is 1. And alpha equals 1 over 2 RC, which is 1 over 2. R is 10 over 11, and C is 2. So we can clearly see that omega is larger than alpha, so we are at this case. Yeah. So, or we can just use technology to, instead of writing everything. Let's take this part, paste it here. Control X. Control V, okay. So this will be our function, right? So what are we gonna solve for? Let's solve for I of L. Or should we solve for V of L? We can solve for either one of them. We can solve for either I or either V. It doesn't matter. But let's say I of L. At the first part, we can assume that we can explain U of T. U of T, it's a function that's value is at 0, and at 0 it becomes 1. So before 0, this function is, so this is a U of T function, and this is time. T1, T2, -1, that's it. Are you guys familiar with still here?
Yes.
Everything is all right? Yes? So yeah. So I'll just assume that I of T at time 0, what is the current at this? So solving for I of T. I of T 0 negative. Just a second, let me confirm that everything is in order with last time. Question 8. Sorry. Should we finish the other LT Spice question first? Because yeah, right. Don't say. Let's go back for the slides. Send. All right. Using LT Spice, plot the instantaneous power for each circuit element of the circuit shown in figure, the same circuit we had previously. Explain how power being transferred in the circuit. So as we mentioned previously, any circuit that has like an inductive or a resistive element, the resistive elements consume power, while the inductive and the inductive and the capacitive elements, their time consumption, average time consumption is 0, right? So in other words, the power has two components, has like an active component and a passive component. And when what you're charged for from the company is only the active part. So the power is a complex value, but its average is always real, and you are charged for this. There is a trick about it. At this level, that's true, but later on, you can see that some elements do consume, for example, motors and generators do consume active parts of the power. So in other words, we can see the results here, but let's do it by ourselves. So start by opening LT Spies. Schematics. For B R C L F3 for wire. The F3. Dot dot PARAMS R1 equals 1, R2 equals 10, C1 equals 2, and L1 equals 0.5, 0.5. So this is one, C1, we have R2 as well. F3, F3, R2. Okay, and C1 and L1. What kind of voltage you guys are you guys familiar? How can we do a unit function in LT spies? L1. So there are lots of loopholes. There isn't one direct way I'm familiar with in how to simulate a unit function, but you can do multiple things. You can do like a pulse, a huge pulse. So that's a unit function. Or yeah, probably that's the easiest one. There are other tricks, but I'm not sure about them now. So V initial is 0, V on is 1, time delay is 0, time rise is 0, time fall is 0 on period 10 seconds, number of cycles, or let's make it this one 20 to be, or 10, it doesn't matter really. And oh, should I move this to the other side? Or it switched for you guys here, but this is my right and this is my left. So that's it. I think How to move an elements. There is something called, there is move. But it doesn't matter. So what kind of simulation are we gonna do? We're gonna have a time series simulation, a transient simulation. So stop time 15, start. That's it, basically. And we just simulate, run. Does not have ground. Run, simulate, run. So explain why the element, right. So how can we plot the power in each element? How can we plot the power in this inductor? So the power is the voltage times the conjugate of the current. In some case, yes.
What were the transient parameters again?
Uh,
Simulated with?
so just 15 seconds. So this is the current, this is the voltage at node 2, and this is the current. So these are them together. We want to create, yes.
Like pause is like 10 seconds, can trace like 15 seconds.
We are just simulating for 15 seconds, and then we can put it 10 as well, same thing. Yes,
How would you put in the parameters?
for
The parameters?
the elements.
Yeah.
I just input like a directive, so edit a spice directive, or either shortcut from your keyboard S or dot, and then dot params. Yes. And then you need to define your elements as variables. So you select the values and do those curly brackets around the name. So that's how we define a variable in LT Spice. Right. Any other questions? So currently we have the volt and the current. We can see that which one is leading. If we can see that the volt is leading, because this is an inductor. So our power is the multiplication of of both. But let's first try multiplying them both. So how to create a notation, how to create a function, right? Yeah. So in some people they right click, and I don't know why there are different things in different PCs in different LT spice, and then they create something like add plot or something like this. For me, it's plot settings, add trace, and you want this trace to be voltage. So it's called VN001, 002, I mean, times I L1. Is this correct? Not really, because it's the conjugate of the current. Sometimes it's the same value, but mostly it's not. So there is a shortcut, con J. I think so. Conjugate. I think I used it somewhere here. There is the shortcut called. Sorry. Conjugate. Is it here? I hate without without a mouse. Yeah, CONJ. Yeah, did we write it correctly? Conj. CO. Then what's isn't it the same thing? Sponge. I'm not sure. Aren't we writing the same thing? VNOO2 times CONJ bracket IL1. VNOO2 times CONJ bracket IL1. I'm not sure what's happening here. I just tested this before coming. So it's the conjugate of the current. So that's the I will is it working for any of you guys? Uh, hmm. So it should be in the videos. But those shouldn't be the currents, those should be the conjugates of the currents. And another thing I did wrong, it's not no, it's correct. So it's correct. So let's try another plot. Let's try plotting the power through this element. So its current is called IC, and you can just get the notation of this element, get the notation of this, copy. Sure. Edit. So you just select the graph and go for plot settings, add notation or add trace. You add trace, and you press your trace, and this is called IC1. But it's the conjugate CONJ. That's very weird. I'll make a video about it and prove that it was just working for me. But let's plot the voltage at the source to make sure it's an impulse, to make sure that it's a unit function. Yeah, it's not. This is another issue. So this one should be it should not be a pulse, it should be a unit function, which is pulse V1, V2 time delay, time rise, sine, exponential function. What's this name? Time value V.
Ten instead of one.
Yeah. V on is 10. And V delay is 0. But this is time delay. V on time fall is 0. Time rise is 10. Let's try this out. So edit simulate run. All right, let's see if I have this or I did answer it previously. Piece price homework 3. And if you didn't piece price draft 4, I didn't save it. But yeah, I'll confirm. So first we have to make sure that we have the input as a pulse. And this is the results I got. But instead of just multiplying the voltage by the current, it's the voltage times the current conjugate. And it should still look something like this, except the voltage should be positive. Like my idea was that like we'll gradually improve upon this design during class. But we start by, I don't know what, trans 300M parameter R 300 mega. No, I don't know what's happening differently. VS1, R1, C1, sine. Oh, that's a sine, yeah. Right, so never mind. Never mind, this is not the same thing. So here it's a pulse, and here I was working on a sine. I will correct it and make a video about it. So another problem we had. I'm sorry about that. So this is 4, 5, and 6, 5. The circuit has a series resistance RS of 50 ohms and the load resistance of, if the impedance of the inductor is 40, what should be the required impedance of the capacitor to ensure the maximum power transfer to RL? So are you guys familiar with this? It should be
It's a big equation, and it's we're trying to solve for the capacitance.
Mhm.
It's like detangling.
Yeah.
Yeah.
So so when does the maximum power arrive to the load? It's when the load and the source are matched. So in this circuit, everything here is the load. So this is all of this is RL and all of this is RS. So when RL and RS are like when they cancel each other, in other words, let's solve for RL and see how does it look like. So RL is equal to let's ZL because ZL is equal to RL parallels to C plus L equals to RL parallels to C plus L, assuming that those are the impedances, those are not just the capacitance and the inductance, equals to RL 1 over J omega C over RL. Is it clear? Plus 1 over J omega C plus L plus J omega L. Right. So in the end, like ZL will have an active component and a passive component. So we want to make the active component to be equal to the active. We want to make so it will have like an imaginary part and a real part. So ZL will have ZL real plus IM ZL. So we want to make this load impedance equals to the source impedance. So equals to RS. So this means that the real part of ZL will be equals to RS and the imaginary part of ZL is equal to 0. That's the whole gist of it. Should we continue? Should I solve it to the end or? All right. I'm not sure what app is best in taking one note. Yes, sure.
So it's 1281.
Do you guys know where is it?
Is it not down the 200 hallway like mechanical engineering one?
Where is that at?
I think if you just like start seeing the like 1-200s or something like that, you just keep on walking, you should be able to find
The
it.
one right here goes to 70, but it doesn't go higher than that. And then the one down there starts at 1300. Well, I'm leaving. I'll help you.
I think
Thank you.
I think they would be experts.
Okay.
So ZL is equals to RL parallels to C plus L, which is equals to RL times 1 over J omega C plus 1 over L. So multiply everything, so equals to RL J omega C. How to, sorry. Equals to, so multiply everything by J omega C, so it will be RL times 1 over RL J omega C plus 1 plus J omega L. So this is, you're solving for ZL. We want to get the real components alone and the imaginary components alone. So we want to remove the J from the denominator. So we'll apply both top and bottom by RL J omega C minus 1 over RL J omega C minus 1. So it will be RL times RL J omega C minus 1 over RL squared negative R omega squared C squared plus minus 1 plus J omega L. We wanna currently divide this into the real and imaginary components. So this is the imaginary component. And this is the real component. So let's take the real component out. It will be negative, or it will be positive 1 over RL squared omega squared C squared plus 1. So this is the real component. While the imaginary component is J times RL times RL J times RL omega C over negative, so let's put negative here, RL squared omega squared C squared minus 1. So plus J omega L. So we know that the real component is equal to 50 and the imaginary component is equal to 0. So this part is equal to 50 and this part is equal to 0. So 50 equals 1 over RL squared omega squared C squared plus 1. And all of this is equal to 0. So we can take the J out. So 0 equals RL omega C over RL squared omega squared C squared minus 1 plus omega L. So did we get anything in the question? If the impedance of the inductor is J40, what would be the required impedance of the capacitor to ensure maximum power transfer? So we have impedance of the inductor is, oh, we could have substituted that from the beginning. So J omega L, let's keep the J. Or we can write here. J omega L is 50. The impedance of the inductor is J40. And RS is 50. And our L is already, we already have the values. J omega L is J40. And our L is 82. That's it. So our L is 82. And we have omega C. So from this one, we can solve for C. Or we can solve for 1 over J omega C. So 50 equals 1 over 80 squared omega C omega squared C squared plus 1. So we just need to either solve for and we need to solve for 1 over J omega C. So from this one you extract. So I wrote them, I expanded everything out, but we don't need to expand it. So we need to directly solve for 1 over J omega C. So in the beginning, it will be much easier. I'll make a video about it as well, I think, to be more clear. But like, I think, do you guys understand the concepts itself?
It was just trying to get like the C value by itself, from just with the, you know, RL plus 1 over J omega C and all that, but.
So we aren't solving for C by itself. We are solving for 1 over J omega C. So it's a much simpler problem.
That's with the impedance of the capacitor, right, to make it maximum efficiency.
Yeah. So we are solving for 1 over J omega C. So it should be straightforward. Should I have to make a new page? Should we still do it, or like what should we?
Yeah.
Yes. Okay, what should we do? The next ones are very straightforward because
Yeah, as I say, it's just the plot.
yeah.
Looking at equations, transformation table.
Mhm. Yeah, so you just plug in the transformation table.
I think me and my buddy just want to. Yeah.
So what sort of videos should I make now for problem 3? Let's go to Zoom.
Sorry, what was your question?
What sort of videos should I make?
If you just upload what you just went through, this,
Mhm.
help room session, that would be
Right.
helpful.